Right, hello Precalculus students. This week we're looking at limits and continuity. And if you remember last time we were talking about piecewise functions and some specific discontinuities. Here we have the definition of a one-sided and two-sided limit, and we're going to do some practice problems with those limits. I'm going to move rather quickly just because I want to get through as many examples as possible. So if you do have questions, please come to the regular scheduled class time or our office hours, and I can help you with those. But let's go ahead and get started here. So a two-sided limit looks like this, written on the right. And now this is read the limit as x approaches c of the function f of x. And here, this is a right-hand limit, and this would be a left-hand limit. Now you can see the only difference, it's very subtle. Let me highlight them. So right here, you can see a little plus, and right here you can see a little minus in the superscript of the c. So that tells me whether or not I'm approaching that value from the left or the right. So if I were to draw this on a number line, so here's c on the number line, and this means that the x values are approaching from the right side of C, so from this direction. Now, for the left-hand limit, it would look like this, where here's C, we're approaching C from the left-hand side, and then for the two-sided limit, it's both of those put together, so you're doing them both simultaneously. So C from the left and C from the right. So the two-sided limit has nothing in the superscript in it. By default means you're considering both sides of the value c at the same time. So for the two-sided limit specifically, we say that the limit exists if the left-hand and right-hand limit, so we'll say two-sided limit, I think I might have taken out the word exists, when, so it equals L exactly when the left-hand limit equals the right-hand limit. So if the left and right meet up at the same height on the graph, then we say the limit exists. So for this first section in Unit 9, Day 1, we're just looking at limits of continuous functions. And for continuous functions, the left-hand limit and the right-hand limit will always meet up. So we're not going to see any where the two-sided limits do not exist here, since all of our functions are continuous. So let's go ahead and plot this function right here. I've already graphed it on my calculator here ahead of time. It looks like this. And I'll go ahead and plot it. So there's a point at 2, 0. And if I plug in 0, there's a point up at 4. And then if I plug in -1, there's a point at 3. So it looks something like this. Since it's a negative cubic, it goes up on the left and then down on the right. So here, they want us to do the limit from the left of the left of 1. So 1, if I plug in 1, or you can use your calculator to look at it, for most of these examples, we will be trying to do it without graphing on our calculator, but here we can trace and plug in 1 to see what the height is. So coming from the left, it's getting up closer to 5. So I drew it a little bit off. It looks more like that. Let's fix it there. So up at 5. So that's from the left-hand side. I'll draw it in green. So the graph is going up to this point right here, and so it's getting closer to 5. Now coming from the right-hand side of 1, we'll follow the graph from this direction. So that's going to be 5 as well. So the height is what we're looking at. We're looking at this height right there, and that height is up at 5. So remember, the limit always tells you a y value. So they each give you this L, which is a y value. Okay. And then here it says, therefore, since the left-hand limit equals the right-hand limit, we can say this limit is 5. And can you do direct substitution? The answer is yes. So if I were to just plug in 1 into this function, you'll see that you also get 5. Okay, let's move on to the next one. Here's a graph of, this is a continuous function. I'll graph it in blue. So here it's of a height -2. So it should be a horizontal line. So there it is, no calculator required. Now they're looking at the limit at 3. So here's the 3, the value at 3 is 2, and coming from the left-hand side of the graph, so we're coming from the left-hand side of 3 right here, so there's 3, and you want to look at the values of the function, the y values, as you get closer and closer to 3. And you notice that the y values are a constant -2. Now coming from the right of 3, look at the y values. The y values stay at -2 until you get to 3. So this is still a -2. So then the two meet up. They are at the same height. Therefore, since the one-sided limits are equal, the limit is just -2. And the answer is yes, you can just directly substitute. All right, good. Let's keep rolling. So here, let's graph this one first. This is a shift to the right by 3. So let's go to the right, 1, 2, 3, and then just draw the standard absolute value graph. There we go. And now they want the limit as x approaches 3 from the left. So here's 3. Coming from the left-hand side, we'll follow the graph. The graph is going down. The y value is getting closer and closer to what y value? Well, the y value there is 0. So notice the height is what we're concerned about. So now let's come from the other direction. So coming from the right of 3, watch the y values. The y values are going down, and as soon as we get to 3, the y value is 0. The left and right limits meet up, so we're at 0, and yes, you can go ahead and directly substitute. If you plug in 3, you just get 0. So this, for continuous functions, is rather straightforward. There's nothing mysterious here. It's for all continuous functions, the answer will just be plugging it in. Except, I guess, we'll see down here for the square root graph, which is a little unique, but so continuous on its domain, I guess I should say. But anyway, we'll look at those. So here, this one is a shift to the right by 4. And this is a cubic, so let's go ahead and graph the parent function for a cubic. Looks like this. All right, that's harder than it looks to make a nice smooth graph that connects those points. Now the limit here, let's look down here. Notice it's approaching 4 from the left. So 4 is right here. I'll put a 4 right there. And you want to follow the y values of the graph coming from the left-hand side of 4. Notice that the y values get closer and closer to this value, which is at 0. Now let's approach from the other direction. Getting closer to 4, the y values get closer and closer to 0. So here they meet up, and yes, you can just go ahead and directly plug in. Square root of 4 minus 4 is just, the cube root of 4 minus 4 is just the cube root of 0, which is just 0. Yeah, so like I said, nothing mysterious there. But here, this is a little bit different. So let's graph the parent function for the square root graph. It looks like this. So now, this the domain of the square root graph, if you recall, is from 0 to infinity, just like that. So here, if we're considering an edge case on the domain, then it only has a valid one-sided limit. So this one, the left-hand limit, coming closer to 0 from the left-hand side, like this, there's no graph. So there is no value of the function as I come from the left. So this left-hand limit does not exist. Now, the right-hand limit, on the other hand, does. As we follow the graph coming from the right, the y values are getting closer and closer to 0. So these two don't meet up. So that means that the two-sided limit does not exist on this edge case of its domain. Now, anywhere else on its domain, it's going to meet up. Like here at 4, the left and right will meet up here at 2, so the value would exist at that point. But as long as one of the two-sided limits don't meet up with the other, or it's not defined, remember, D&E represents does not exist. And if that's the case, then the whole limit itself will not exist. So in this case, the answer is no. You can't quite just plug it in and get your answer, because if you plug in 0, you'll get 0, which is the value of the function, but not of the limit. So here's another one. It's just a shift of the square root function to the left by 3. So let's go ahead and plot that. So up here, that's to the right 9. So if you count these spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, up 3, I'm just plotting the parent function shifted to the left by 3. So here's our square root graph, and we're considering the limit at 1. So the limit is right here, or the value, limit value. And coming from the left of 1, the value of the function goes up to 2. And coming from the right of 1, right here, the value is going up to 2. So does the limit exist? Yes. And it's just 2. And can we go ahead and plug in 1 into the function? Yeah, if you plug in 1, you get the square root of 4, which is 2. So the punchline is, for continuous functions, it's always going, the two-sided limit will exist unless it's at an edge case on its domain, like the square root function. So something like these here, we can do without even graphing the functions. This is a line. Lines are continuous, and we can just plug it right in. So this is going to be 3 times 3 minus 2. That's 9 minus 2, or 7. So we're just plugging in the limit value in for x. That's all we're doing. So nothing spooky here. The next one, here there is no x, so I have nowhere to plug in this negative 2. So it doesn't really matter what this number is down here. The limit will be 3, always. Here, if I try to plug in this 4, this is a shift to the right of the square root function. If I try to plug in the 4, we'll notice that you get the square root of 4 minus 6, which is the square root of negative 2, is undefined. So this limit, instead of writing undefined, which we don't want to do that because that's for functions. Functions are either defined or undefined. Limits either exist or do not exist. So we'll just write D&E. And that's because the function is going to be undefined when I plug it in. Here, now this one is on the edge case, and it's probably easier if you just look at a graph. So let's do a real quick graph. This is a shift to the right by 6 of our square root function. So here's our square root function. And we want the limit from the left of 6. This one's actually from the right of 6. So coming from the right of 6, we want to follow the graph. And it's getting closer and closer to 0. Now coming from the left of 6, that's for number 11, there is no function. It's not even defined over here. So this one is D&E, which means this one here is the two-sided limit. Again, remember, you have to look at that little plus and minus in the superscript to let us know whether or not this is from the left or the right. This one here has no plus or minus in the superscript, which means it's two-sided. So we have to look back at these two limits to consider that. So since they don't match, then the final answer here is D&E. It does not exist. The one-sided limits have to be equal in order for this two-sided limit to exist. Okay, good. Let's keep moving. So again, we're continuing with continuous functions here. So for some function f here, this is not a continuous function. So I guess we're starting into discontinuous functions. I guess this is still in the first day's notes, but that's okay. So here, f at 1. Now, notice here the function is defined everywhere on its domain, or everywhere on for all real numbers. Even at 1, the function's defined right down here at -1. So f of 1 is -1. Now, this is the limit going to 1 from the left. So coming from the left-hand side of the graph, we'll follow the graph. And you want to look at the y values. So what are the y values getting closer to as I approach 1 on the x-axis? Well, as I approach 1, that's coming from the left of 1, look at the y values on the graph, and they are getting closer to 2. So that's coming from the left. Now let's come from the other direction. So let's come from the right. So coming from the right of 1, that's from this side, from the positive infinity direction. As I come down the graph, I'm looking at the y values getting closer and closer to the x value of 1. We see that it still approaches 2. So since the one-sided limits match, since they're equal, that means that we can say that this two-sided limit, notice that there's no plus or minus in the superscript, so that means it's two-sided, is also a 2. So all three of these limits are equal because the two-sided limits are equal. So what is the limit at 0? So coming from the left of 0, meets up right there, and coming from the right of 0, it also comes to that same spot. So coming from the left and right, the y value at this spot is 0. So here's another tricky one with a discontinuity at -1. So you can see this jump discontinuity. So if I plug in -1, it is defined. It's defined right here at this solid point, which is up at 4. Now, coming from the left of -1, let's follow the graph. Coming from the left, and as I approach -1 here, what is the y value getting close to? Well, the y value is getting closer to 0. It's getting close to the x-axis. So now let's look at the limit coming from the other direction. So coming from the right side, as I approach -1 here on the x-axis, what happens to the y values? Well, it looks like they're getting closer and closer to, I think that's a 2. So let's go ahead and put that there. So getting closer to a 2. These one-sided limits do not match. So this two-sided limit here is D and E. So approaching -1 from the left and right, they do not meet up. So the answer is D and E. On the next one here, they just say, what is the limit as x goes to 1? Well, let's look at 1. I might have to erase some of the graph here. 1, it is right there. So coming from the left and right sides, the graph does meet up right there at -2. That's the y value at that point, at 1. So there's no break in the graph there. So the two-sided limit does exist, and it gives me a -2. They meet up at that height. So just to recap, we are always giving y values. These are always y values for our function. So this is a y value. This is a y value. All of these are y values. So we're looking at the height of the function coming from the left and right side. Okay, well, let's go ahead and continue. So now this is the next day's notes, day 2, and I'm trying to keep this lesson relatively short, so I am moving quickly, so I hope that I can get it all under 45 minutes for you. So now here, we're actually starting to look at some graphs that have discontinuities. Just like the last two, except here, we're actually graphing them. So let's go ahead and graph the 1 over x graph. It looks like this. And there's a point here. And there is a vertical asymptote right here at 0. So 0 here is a point of interest. We're interested in what happens right there at 0. So here, what is the limit as x goes to 0 from the left-hand side? So from the left, that's from this side, let's follow the graph and get close to 0. And the graph is going down. So as I get closer and closer to the vertical asymptote on the left side, that means we're going to -infinity. Now let's come from the right side of 0. That's going up to positive infinity. These two do not meet, so this is D and E. Now technically, infinity and negative infinity is also d and e. It doesn't exist because infinity is not really a real number. So when we say infinity and negative infinity, we're being a little bit more specific than d and e. We're saying, hey, it doesn't exist, and by the way, it approaches infinity. Infinity and negative infinity is a type of d and e. It's just a more specialized and more specific d and e. So don't get confused here in thinking that these mean that the limit actually exists. Okay, can I directly substitute here? And the answer is no, you can't, because the function will be undefined if you try to directly substitute. Is there an algebraic method for this? No. What you could do is if you're plugging in a number like 0, you could say like negative 0.00001. So this is like the left side of 0. This is getting really small. So it's like 1 over small, which is this blows up and gets very, very large. So there's really no algebraic method. This one is really done analytically, so we'll just say none. So let's have a look at number 2 here. So this graph has a vertical asymptote at -3. You set the denominator equal to 0 and solve. So x equal -3. Let's go ahead and drop that vertical asymptote in. It's also got a horizontal asymptote at y equal, remember, if you look at the coefficients, this is a 1, 1. They both have the same power of x. So the horizontal asymptote is right here at 1. There was a horizontal asymptote for this last one at 0, if you were wondering. And we also have an x-intercept. If you take the numerator and set it equal to 0, you find the x-intercept. So that's going to be right here at x equal 1. It's going to cross. And this graph, it's not going to cross the horizontal asymptote at any point. You can check by setting the graph equal to the horizontal asymptote, like this, multiplying the denominator to the other side, and then solving here. So we're going to get -3 equals -1, which is never true. So this graph never crosses the horizontal asymptote, which means that the graph has to look like this. So it's got to approach that way. It can't cross the horizontal, and it can't cross the vertical here. So now on this side, will it be going up or down to infinity? You could check by plugging in -4. That's a valid option. Or since the root here, or the vertical asymptote has a multiplicity of 1, this factor has a multiplicity of 1, that means that this is going to alternate signs. So it's going to be up here. You could check by plugging in -4 as well. You'll see that you get a positive number up here somewhere above the horizontal asymptote. Okay, so enough work there. Let's go ahead and check our limits. From the left side of -3, like that, the graph is going up to positive infinity. And from the right side of -3, that's going down like this. That's going down to negative infinity, which means that this final limit is simply just d and e, because the left and right hand sides do not meet up. And no, you cannot directly substitute, but there is an algebraic method, or more like an analytical method, like the previous one. So if I take the limit as x goes to -3 from the left of x minus 1 over x plus 3, you want to think about plugging in a number like -2.99, something a little less than -3. So if I'm plugging in a number a little less than -3, the numerator is going to be negative, and the denominator is going to be positive. So we know, because this is going to either positive or negative infinity, because this is at the vertical asymptote, we're looking at the limit at -3, where the vertical asymptote is. We know it's going to be either plus or minus infinity, and because this is going to be negative over positive, that implies that it has to be negative infinity. Oops, did I do this wrong? Looking from the left of -3, whoops, I did this wrong. So left of -3 is 3.0001, a little bit more negative than -3. So this is going to be negative over negative, which is positive. My graph was right, but my analytical limit here was a little incorrect. So you really don't have to do this, but it's a good way to think about it in your head. It's very similar to just plugging in -4 into the function. The only difference is we're plugging in a number much, much closer to the vertical asymptote. So it's like we're taking the limit in our heads, which is a little harder because this is a little bit more specific than just -4. But it's a better method. It's a more calculus-based method that you'll be using next year. Okay, let's try the next one here. I'll go ahead and graph this one. So there's a vertical asymptote at -1 if you set the denominator equal to 0. And if you look, the highest power of x is in the denominator, which means the horizontal asymptote is right here. So if you do the analytical limits again, plugging in something a little bit less than -1, like -1.0001, excuse me, is plugging that in, the denominator is going to be positive, and the numerator is negative. So that means this is going to negative infinity. We know it's going to be infinity because we're looking at the vertical asymptote. So the question is it positive infinity or negative infinity? Because the numerator is always negative and the denominator is always positive, that means it's going down to negative infinity. Now, I know it doesn't cross the horizontal asymptote because our numerator is never 0, which means we have no x-intercepts. Now, checking from the other direction, we want to plug in a number like -0.9999, so a really small negative number to the right of -1. And if I plug this in, I'm going to get negative in the numerator and positive in the denominator, which is, again, going in a negative direction. So this is going down to infinity, just like that. So both sides are going down to negative infinity, so this is also negative infinity. We can't just directly plug in the -1 here because we're going to get undefined, so that doesn't work. And the algebraic method, there's really no algebraic method here other than what we're doing mentally. So this is called analytical evaluation. You're just thinking about it. There's really no work that needs to be shown on the paper, which is why I hesitate to even write that. So you don't have to show me that on your homework or tests or quizzes. This is something that's done mentally that I like to write on the paper so you can both see and hear what I'm thinking. Okay, let's try the next one here. Before we evaluate the limit and before we graph it, let's factor the denominator. And this x -2 factor is going to cancel. So in the limit, we can remove that factor because it will not change the limit. Is going to be 1 over x plus 2. So now let's go ahead and evaluate this. So that means that there is a hole at 2. So we'll say, maybe above this, we'll say hole at x equal 2. So when we go to graph this, there's a vertical asymptote at x equal. So if you set the other factor equal to 0, you're going to get -2. So we have a vertical asymptote at -2. Let's make that straight. And since the highest power of x is in the denominator, we have a horizontal asymptote at 0. And we also have a hole at x equal 2, which is right here. And if you plug in 2 into this final function, it's at a height of 1/4, positive 1/4. So let's put a hole right there. So that's by plugging 2 into the deleted form of the function. So after you delete the factor that makes it undefined, that is the hole, you can plug in the x value at the hole into the remaining part of the function to help you find where that hole is. It's up at 1/4 after we plug in the 2 here. Okay, so let's go ahead and connect our function here. It's got to be above because the hole is above. And over here, it's going to be down on this side because the multiplicity of the -2 root in the denominator here is only 1. The signs have to switch. So like this one, notice that the multiplicity of the root in the denominator was 2. It's even, so they both go the same direction. Whilst here, since the multiplicity of this root is 1, they're going to go in opposite directions, or the sign will change at that root. Okay, so what is the limit coming from the left of +2? It's going to right there at 1/4. And coming from the right of 2, right here, it's getting closer to the height of 1/4. Therefore, the final limit is just 1/4. And can you do direct substitution? Well, yes and no. You might have to, so I'll say factor, then yes. So you have to do direct substitution after you factor. So algebraically, the work would look like this. So if we're doing the two-sided limit, x minus 2 over x squared minus 4, you factor and cancel like we did above. So it's going to be 1 over x plus 2. So just like we did up here, factor and cancel. And then you can go ahead and directly substitute this 2 into the place of x. So we get 1 over 2 plus 2, or 1/4 is the final answer. Notice some key development here. The limit disappears as soon as I make that substitution. As soon as I plug in the x equal 2, that limit is gone. So that once that direct substitution has taken place, you stop writing the limit. So many early pre-calculus and calculus students keep writing the limit, or they maybe don't forget to write the limit. Right here is the step where the limit should disappear, because we're replacing that x value with a 2. As soon as you quote-unquote take the limit or plug in the number, is when the limit should disappear. You've done it, it's gone. So yeah, that's the final answer for that one. Let's keep rolling. Yeah, okay. So how are we doing on time? Okay, so I'd like to try to finish up in maybe somewhere around 10 minutes from now. So let's just get through what we can get through. So the first one here, if I plug in x equal 5 in the numerator, we're just going to get 0. So let's go ahead and try. You should always try direct substitution first. So this is going to be 5 minus 5 over 5 minus 2 is 0 over 3. Is this undefined? And the answer is no, it's not undefined, it's defined. 0 over 3 is just 0. And so here, direct substitution works. So we can say directly substitute. Here, if you try to plug in -2, let's try. You can just watch. You don't have to write this down as I write it down, because I have a hunch that it's not going to work. So here this is going to be 4 minus 4 over -2 plus 2 is 0 over 0. This is undefined. So what that means is direct substitution doesn't work. Does not work. So we're going to have to do some type of factoring or algebra. So you should always try to just directly replace the x with the -2, or the limit value. That's the first thing that you should always try. And when inevitably it won't work, like you get an undefined solution, then that means you have to try some algebra. So let's try to factor this. So we'll factor the numerator. It's going to be x plus 2 and maybe an x minus 1. Yeah. Notice that the x plus 2 factor cancels. I meant to get red. But the x plus 2 factor cancels. And so we haven't directly substituted yet. So we haven't plugged in the value into the function yet. We canceled. So let's write what's left over. And notice the limit is still hanging around. The limit will stay here until we've directly substituted. So let's try to directly substitute now. So after you've canceled something, this was the problem. As soon as we cancel that problem and try to plug in the -2, we're going to get -3. All right, so that's the answer. So you can't use direct substitution here until you factor and cancel. All right, let's try to do direct substitution here. 5 minus 5 over... This is the same one as the one above. How did I miss that? Oh, this one was from the right side, and this is a two-sided. The work doesn't change here. The work is going to be the same. Still 0. So your one-sided limits, you can still evaluate directly if you can plug it in. So the problem becomes if you can't plug it in, then you have to do some algebra. You might even have to graph the function to see what it is on the left side. You might have to plug in a number slightly less than 5, like 4.999, or in this case, slightly greater than 5.00001. So you're always looking at a number slightly bigger or slightly less than the number that you're trying to plug in. So here, this one, -2, let's go ahead and try to plug it in. And if it's like the one from above, which it's exactly the same, we just do both. We have to first factor and then cancel. So I'm just going to go ahead and limit as x goes to -2. This is the exact same problem. X plus 2 over x minus 1. And then the work is going to be identical. There's really no difference when you're doing algebraic work between one-sided limits and two-sided limits. They're going to be exactly the same. Okay, and so then here, once we plug in the -2 into what's left over, so we want to plug in the -2 right there. Let's rewrite the limit for practice. Limit Sx goes to -2 of x minus 1, and then plug in the -2. Now, notice the limit goes away as soon as you plug in the limit value, so it's going to be a -3. Should be the same as this one. All right, so let's finish this out. See what we can get through. I think we have maybe about 5 or 6 more minutes left. So these are very unique limits. Let's actually take the time to plot this on a calculator real quick so that we can see what this function is actually doing. It does say graph without a calculator. Maybe we should do it without one. So what is the absolute value? Let's just plug in a couple of numbers here. So if I plug in something like 5 in for x, then I get 5 over 5, which is 1. So over here at 5, it's up at 1. Well, what if I were to plug in something maybe like 0? It's undefined, so we don't have at 0 over 0, which is undefined. So what if I plug in 1? 1 over 1 is 1. I put that up at 2. At 5, it should be up at 1. If I plug in 2, it's up at 1. So you can start to see a pattern here. At 0, it's undefined, so let's put a circle there. And then everything to the right of that is up at 1. So I wonder what it's doing over here on the left-hand side of the graph. So let's plug in something like -1. So -1, absolute value of -1 is +1. And then over -1, so +1 over -1 is -1. And then it's going to stay -1 for all the subsequent negative values. So here at 0, we'll put an open circle just like that. And go to the left. So this is a step function. It steps up 2 units, and it's centered at 0. Unit step. So, so here, let's look at this limit. It's pretty easy to answer once you've got the graph. This limit coming from the left of 0 is -1. Let's use, so you can follow the graph, and we want to look at the y values. So we have a -1. But coming from the right, you follow the graph here, the value is up here at 1. The y value is 1. So the limit at 0 is d and e, does not exist. because these two steps don't equal. There's a jump, there's a gap. So can you directly substitute? The answer is no. Can you evaluate algebraically? Yes, it's a little bit complicated to evaluate algebraically. It would look something like this. Coming from the left, the absolute value function, we have to look at the piecewise branches. So it's x when x is bigger than or equal to 0, and it's negative x when x is less than 0. So here, since we're less than 0, we want to replace the absolute value with the negative x branch. So it's going to look like the limit as x goes to 0 from the left of negative x over x. The x's cancel, and it just leaves us with limit as x goes to 0 from the left of just -1, because the x's cancel, which if you try to plug in this, there's no x's left to plug it into, so we're just going to have -1 as our final answer. So that's coming from the left-hand side. And you can do a very similar argument on the right, just replacing this absolute value with the positive x. So the limit as x goes to 0 from the right of the absolute value of x over x is going to be the limit as x goes to 0 from the right. So coming from 0 from the right, we're on this top branch, which is going to be x over x. Those cancel and just give me 1. So there's the left and right hand limit algebraically. It's a little bit of work to do it that way. So graphically might be the best way to do these. These are fairly complicated limits. They're not easy by any means, so I can't pretend like they are. So here, what does this do? This is a shift right 3. So let's graph the exact same graph from number 11, just shifted to the right 3. Okay, there we go. And of course, we're considering the limit at 3. So coming from the left of 3 is -1. Coming from the right of 3 is 1. That's right here. And then the two-sided limit doesn't exist. And can you directly substitute? No, you can't, because if you try to plug in 3, you're going to get 0 over 0, which is undefined. So algebraically, what does this look like? It looks exactly the same as this one. The only difference is the piecewise absolute value of this function. The only difference is what this function looks like. So you replace it with x minus 3 if x is bigger than or equal to 3, and you replace it with x negative x minus 3 if x is less than 3. I think this might be a little bit much to do, so we'll only look at this a couple times. How are we doing with our time? I'm about out. So I think on this next page it says optional problems if time, which we don't have time here. So let's maybe just do one of them. And then maybe during class I'll start by doing these with you guys if we have time, or if you guys are okay with that. Maybe we'll do homework problems or whatever. But let's try one of these hard ones like this one right here. So what we want to do is first define the piecewise function for the absolute value of x minus 2. So we just did this, except with x minus 3, so it's going to look very similar. It's x minus 2 if x is bigger than or equal to 2, and it's negative x minus 2, negative x minus 2 if x is less than 2. So let's go ahead and do the one-sided limits here. So the limit as x goes to 2 from the right is going to look like, let's just go ahead and take the top piece, x minus 2, because we're coming from the right, that's bigger than 2, and then the bottom piece stays x minus 2. So the x minus 2's cancel, and we're left with just 1. So this is the limit as x goes to 2 from the right of just 1 is 1. Now, checking the other direction, from the left, we want to replace the absolute value with the top piece. So x minus 2, x minus 2. Now they cancel again, so these factors are going to cancel. But what's left behind is not a 1, but a negative 1. So we're going to be left with negative 1, so we get negative 1. The fact that these two don't match, so you could say not equal, not equal. So that means that the two-sided limit does not exist. Does not exist. This one here, we're considering only the left-hand side. So what that means is you would replace this, the top piece, with the negative of the top. So we want to replace this with the negative x plus 4 with its piecewise absolute value definition. Looks like this. And then it's negative x plus 4 if x is less than 4, negative 4. So those are the two pieces of the piecewise function. And so you just want to choose the appropriate piece for whichever direction you're coming from. So those cancel, and we're left with negative 1 is the final answer for 13. They only wanted the left. They didn't want the two-sided. Here we had to check both because this is a two-sided limit. Yeah, I think that's enough for today. I'll upload this to YouTube, and I will see you guys in class this week. Thanks for watching.